Alright, so what is Euler's method? Euler's method is a technique which gives us the approximate answer by continuously updating the solution at discrete points in the domain, giving us a rough estimation rather than the exact solution. For example, let's suppose we have a differential equation set up over here, dy over dx is equal to y. When y is equal to 1, x is going to equal to 0. And if you differentiate this out, you're going to get y is equal to e to the power of x plus c. Then I form three variables, which is x, y, and dy over dx. If I give h a step size of 1, then my x value will be increasing by 1 each time I substitute it into the table. So you can see 0 plus 1, 1, 1 plus 1, 2, 2 plus 1 is equal to 3, and so on and so forth. Y is equal to e to the power of x. So when x is equal to 0, y is going to equal to 1. And if you assume that the gradient is a constant, the dy over dx is going to equal to y. And if y is equal to 1, dy over dx is going to equal to 1. Take note that the smaller your h value is, the smaller your approximation error will be. I know you have a question. How do I find my y values? The y values here, like 2, 4, and 8. And my answer to that would be by using Euler's method's formula, this one right here. So when x increases to 1, we know that the h, which is our step size, is 1. The previous value of y would be 1, and dy over dx would be equal to 1. Thus, using the formula, we can find y, which is 1 plus 1 times 1, which is going to equal to our y, and y is equal to 2. And since y is equal to 2, dy over dx is going to equal to 2, and we can carry on and continue doing this until we have our values here for our table. Now we can go ahead and plot our graph. From here you can actually see that Euler's method gives us an approximate curve that is close to the actual curve of y is equal to e to the power of x, and this also shows that Euler's method gives us the approximate values and solutions to help us solve the questions and reinforces my definition of Euler's method. Alright, so now we're going to be using Excel sheets to solve the IVP for when dy over dx is equal to x squared plus 1, where y is greater than 0, given the initial value that when y is equal to 1, x is going to equal to 0. Let's find the approximate value of y when x is equal to 1. I've set up this table over here consisting of three columns, x, y, and function of xy. Keep in mind that function of xy is equal to dy over dx, so these two are the same thing. I've used a step size of 0.1 for a smaller approximation error, as you will see later on. And my initial values of x and y will be 0 and 1. I've calculated my function of xy value by using this formula right here. Dy over dx is equal to x squared plus 1 over y. So I just squared my x value, so 0 squared plus 1 divided by my y value of 1. So now moving on towards my x column, how I got from 0 to 0.1, 0.2, 0.3, 0.4, yada yada yada. I made this little simple formula right here. So I took my previous value of x and added it by the step size of 0.1. And for my y value, what I did is I implemented the Euler's method formula into Excel. So I took my previous value of y, I added my step size to it, and I multiplied it by the previous value of my function of xy. And this is exactly how I got my current y value. So I just made this little formula here. And then for my next function of xy value, I just repeated my steps for this one. So I took my x value of 0.1, squared it, added 1 to it, and divided it by my y value of 1.1, as you can see in this formula here. Now, all that's left to do for my table is just to drag everything down using Excel's functions. You can just do this, this, and this, and boom, we have all the values we need. Okay, so now we can find the general solution for the IVP, where dy over dx is equal to x squared plus 1 over y. And if we integrate this down, and we say that y is greater than 0, and make y the subject, we will get y is equal to the square root of 2 over 3x cubed plus 2x plus c. Now, using the values from the question, where x is equal to 0 and y is going to equal to 1, we can find a particular solution, which will give us c is equal to 1. And using that, we can find the solution for y when x is equal to 1. We can just do some good old-fashioned substitution, and we'll get the value for our calculated y as y is equal to 1.91485, which will just round up to 1.915. Okay, so now we have our approximate y value and our calculated y value. This is my approximate y value, by the way. The highlighted thing and the calculated y value is the thing we just solved for. We can find our approximation error by subtracting our calculated y value from our approximate y value, which will give us an approximation error of 0.00366249, which is pretty damn accurate. Here I just made a new table where I just show you the effect of a lower step size. Essentially, a lower step size will give you a lower approximation error, which will make your entire graph more accurate. The takeaway from Euler's method is that the smaller our step size, the more accurate our results are going to be. However, we will have to do more steps, more calculations to get to that result.